Hi, I'm Stephen Chen. I'm currently the Director of Machine Learning at RBC. Before joining RBC, I was a management consultant where I helped many organizations transform their data science teams for greater productivity and efficiency. So today I'd like to distill down, all the experience and practice into a few principles for you to apply to your own teams. So according to Gartner, only 20% of machine learning and AI develop business outcomes by 2022. And this for a bunch of reasons. Budget challenges or overruns, platform instability or immaturity, the ML team is difficult to work with, or business distrust. The ML failed to deliver results, or ML overpromise, struggle to push to production, or scale up to production. Little control of externalities, little support from senior management, and time resource crunch, and etc. And what really attracted me to RBC was that I had all these problems to tackle. Uh, so my predecessor made a bunch of overpromises and left with nothing built. The platform was constantly crashing, and everything needed to be overhauled. And there are a number of ML teams in RBC, but mine was lagging and on the hook to deliver incremental revenue, and we were behind target. Yet in just a year, we managed to surpass all the other ML teams and became the only ML team to deliver tangible business results at RBC. So what did we accomplish? So by working with existing constraints without increasing the budget, we became the most productive ML team RBC and probably Canada. Because in the first 6 months alone, we pushed 60 models in production versus 13 in the past 3 years. And we are on track to deliver over 100 models in 2021. On top of that, the models were showing a 13 to 45% model improvement over what was built previously. And in a head-to-head comparison of a hot AI firm, we beat them by 2 times. On top of that, we also managed to gain cost savings and ROI by achieving 8 times decrease in compute, a third decrease in model scoring time, and 10x storage reduction. And the outcome was we surpassed the aggressive double-digit incremental revenue growth target by 20%. So all of which is to say is I believe that these principles will be broadly applicable to any problem you might have with your own teams. So the first thing is know the best practices. And what I mean by best practices is not, I don't mean the best practices that you develop yourself, which are meaningful because they're specific to your own circumstances and develop from what you've learned or refined. These best practices are the ones that are kind of the generic ones that are coming from white papers, from vendors, from platform promises. And I think that's partly why organizations fail to achieve ML productivity because they're always chasing that silver bullet by replicating others and not realizing that due to the divergence in problem, situation, and underlying data, it's probably a suboptimal solution for them. So the other thing to remember as well about these best practices and case studies is usually sample one, right? There's a publication bias. No one's going to publish a paper or case study of what did not work. And so you always need to read through them and evaluate them in the context of what you have in your specific situation. And on top of that, don't fixate on low-hanging fruit because they rarely integrate or scale into long-term solution. The quick wins mentality, I find, prioritize hacks that have to be redone. And so it's very important that what you build in the short term should be a foundation for the long term. Secondly, don't wait for Godot. And I put SageMaker as a joke. Waiting for Godot is a play by Samuel Beckett in which two characters argue about stuff of no consequence, really, or waiting for Godot to arrive. Who never does? And so I think it's a great metaphor for the trap that many teams, I think, I observe fall into, whereby they keep debating on what's the next big thing, and in the process are trapped in this cycle of inaction. So and I put SageMaker because when I joined RBC, SageMaker was the Godot for RBC, and while the other ML teams were debating about SageMaker, my team quietly blew past them. So the key thing to know is to work with and integrate what you have and don't devalue legacy systems or old guard employees. So build around your workflow and infrastructure versus waiting for some sexy new tool to fall in your lap and build around it. And third, don't drink the Kool-Aid. This is what I call the overpromise or the so-called magic of AI versus the limits of your data. Focus on pragmatism over Pollyannism. So a funny example would be when I joined RBC, one of the models and programs I inherited was trying to predict which of the RBC clients were thinking of starting their own small business. And I'm like, that's nice, but I don't have thinking data. So we actually have to reframe the problem to figure out what actually is compatible that we have access to that we can actually build a model against and to track against. So instead of focusing on low-hanging fruit, the typical reaction tends to be, let's do the big picture strategy. And that's actually not the first thing you should do. The first thing you should do is to fortify integration points. And because those are points of failure. Now, what do I mean by integration points? So I'm going to use this analogy where the ML team is the dam that's holding back the water and generating electricity for downstream users, as well as clean water for downstream use cases. So your integration points are what flows in and out of machine learning. So a lot of times people focus on what's coming in, but they neglect what's coming out. So it's very important to understand how your users are using data, how they want to use the data or models that you're producing. Because you can build a fancier dam, but if you're not fixing, say, the power lines and the flow gradient of your output flow, those people are not going to experience any net benefit from any improvements you make. So it's always important to fix these integration points, the outflows as well as the inflows. So this is also kind of a caution to scale appropriately, because this is very tempting to start building the dam, your ML team, and scale it way beyond what you actually need, what your users need, and actually what your data can support. So it's kind of like building a Hoover Dam when your data is kind of like a muddy creek. It's not going to work. It's not going to give you any net benefits. You need to scale appropriately. So when I joined, my team was actually a source of errors and delays, but because we scale appropriately and fix our integration points, we actually now catch upstream errors before they pass downstream. So, and the other thing to know is don't bleed on the cutting edge, what I call bleeding out for ego creds. We know that a lot of what's published in academia is really not applicable because they use artificially clean data and censored results. And also back to what I talked about, publication bias, whereby they only publish the successes and not what failed. So a good example would be when Google had developed the cutting edge blindness detection technology and algorithm. So there are many articles hyping about how it did better than doctors and transforming healthcare, et cetera, But there are only two mentions of what happened when Google deployed it in market. When they deployed it in the field, it failed. So again, be very cautious, because a lot of these white papers and cutting edge stuff that's being promoted have never been deployed in field in practice. So you need to approach them with a sense of caution versus relying on the results that they promised. So my analogy of that is, it's kind of like Ginzu infomercial. All these sexy new things, they show I can cut a tomato and you can cut a can, I can cut a pipe and things like that. But that's actually not what you want in order to scale your ML productivity. What you need is actually a good foundation, right? So the problem with fetishizing the new and unstable is this cutting edge cuts both ways. It's a double-edged sword, because first of all, it's a production risk, and it tends to be fairly unstable. So you almost trap in POC hell, whereby you're spending a lot of resources trying to get the system to run the way you want it needed to run, versus building good foundation to build more things on top in the first place. So the focus should be on stabilizing your platform pipelines first, and building scalable and replicable pieces for controlling sources of misinformation and error. And the reason why I used the foundation as an analogy is, foundations are not sexy. They're the least visible part of building, but they're most important because they determine the extent you can build and the outcome of what you build. So for example, for my team, we cut down the lead time from model dev to dev start to production from months to just weeks by building new pipelines that reduce errors and instability. So like I said, in the past, we were the source of errors and delays, but now we're catching and fixing upstream errors and delays. And so what these replicable and scalable pieces has enabled to do is free up resources on high value work, such as more R&D and continuous improvement, versus always having to debug a crashing platform or crashing model or something that's happening. Next, don't toss shit to see what sticks. Now, shit is basically what I call a subjective, haphazard, inconclusive trial. And this is what I call the Kaggle mentality. You try different things to see what works. And you get that from new data scientists as well as some executive higher ups, because this is mistaken notion that, if you try many different things, then it's going to be the magical thing that's going to solve all our problems. That may be the case, but it's working by accident, not by design. And you're wasting a lot of time and resources, and such as troubleshooting and doing random searches basically. And there's no applicable learning that you can apply to your next problem. So essentially, we want to tackle a problem as a surgeon versus surgery Sam. So if you recall when we mentioned we did a head-to-head test with a leading AI firm, so we went with a surgeon approach and they went with the surgery SAM approach because they had fancy auto MLs, fancy algorithms. You're trying all sorts of different things. And yet we beat them 2x on a difficult rare event trend problem. And the key thing to know is that, when you're doing a kind of search, superficial search, I call it, it doesn't improve over time because if they rehash the same search space over and over again, whereas the surgeon improves over time. And so what we did was we had a structured exploration whereby we were learning from what we did and tested and then derived learnings for the future. And basically part of it is knowing when to push further or drop something when it does not work. And also the other thing about the surgeon is, the reason why a surgeon is successful is not because he or she is using the latest tools, but they're keeping a patient alive with really, standard technology like valves. And so this comes to this leads nicely into the point, which is patents come and go, but principles persist. So what do I mean by patents? So these are things like, the buzzwords of the day, like agile, Kubernetes, containers, you name it. So if you've been in the industry as long as I have, you realize that these are all, fashionable things. They're novelty right now. I mean, they're fashionable right now for a specific reason, and they'll probably be less relevant in the future. The problem with that is it costs a lot to rebuild and to hop onto another bandwagon. So rather than putting all your eggs in the latest agile Kubernetes container Docker whatever basket, recognize that there are core principles that your architecture models have to adhere to, regardless of what the latest and greatest patterns are. So the principles have to persist. So a fun anecdote I have was when an intern from another team was trying to apply machine learning to a problem, he did not respect, fundamental principles of independent variable, and he actually got a model that had a negative R-squared, which I've never seen before in my life. And I actually did Google quite extensively to figure out what negative R-squared means. It actually means it's worse than random. Imagine building a model that's worse than random. So I want to focus on two key principles, which I feel are quite important in the current environment, but have been kind of neglected due to the current fashionable way of doing things. The first of which is the power parametric models, so-called classical methods. There's lots of Medium articles that says, like, I tried regression, didn't work as well as random forest XGBoost, blah, blah, so this is better. The problem is, a lot of times those are false analogies because it's very difficult to build a proper parametric model. It's strict assumptions must be met, and it requires experience and domain knowledge. So you can't it's not a computation solution. It's a fairly rigorous exercise. So, but if it's built properly, a parametric model is way more stable than a non-parametric model. And this is especially important when we're thinking about what's happening during COVID, which has broken a lot of models, almost all which are non-parametric, and think about how we're going to rebuild for COVID and beyond. And so I'm using this as an illustration to show the power of parametric models. This is not built properly. This is just a sample simulation I did, but I think it should demonstrate the point. So what I did is I took a sample data set, which was a Wisconsin diagnostic breast cancer data set, and basically trained a logistic regression model and a non-parametric, such as random forest or XGBoost model as well on the same data set. But in the test set, what I did was I started increasing the amount of noise and bad labels. Basically, I flipped the label, so it's a wrong label. And so when that happens, you expect the model to break down. So on the left-hand side, you can see that as the noise increases, so it's roughly 0 to 10% noise. I'm introducing data set. As noise increases, you do see some divergence in terms of what the model's predicting for logistic regression, but it's still very stable. It's still within the same range. You can look at the distribution; it's centered around the same, still centered around the same area. On the right-hand side, when you apply the same thing to a non-parametric model, such as a random forest or XGBoost, something very interesting happens. It starts bifurcating. It splits into two, right? You can see up, down, up, down, up, down, up, down, like this for any point in time. And the paradox is, when there's a lot of noise in data, it reports a high accuracy. So basically, it's doing a better job at predicting a bad label than a good label. So this is something to be very careful about when you're evaluating a non-parametric model in terms of whether it's still good enough for COVID, or thinking about rebuilding those models. Secondly, is what I call the Hummer versus Hyundai thing, which is the principal parsimony. And what I mean about that is the Hummer is, all the fancy bells and whistles, big truck and everything, versus Hyundai, not really fashionable brand or anything, but better fuel efficiency. So it's really the contrast between a bells and whistles versus efficiency. And the reason why I bring this up is because I think there's a tendency to boast about or measure on the wrong thing, such as, oh, we have 1,000 features in the model, we have 500 containers running, so it's better. It is not. For example, we replace a random forest of over 500 features with a logistic regression with only 20 features, and we accomplish 40% model improvement and stability. Right, the principle of parsimony is less is basically more. And this is a good illustration of more versus less. When you have more, like more inputs or more complexities, you're going to introduce lots of more noise. And obviously more complications when something goes wrong, because when there's more knobs to twiddle, when shit hits the fan in production, there's really no way to know what you need to fix. So having a more complex model and having more complex architecture and setup is a hurdle to robustly scaling your ML practice. So again, if you desire to scale up and be more productive in machine learning, it's much better to adopt a parsimonious approach whereby the most efficient expression of the model architecture is possible. Finally, optimize for actuals, not abstractions. And this is integral to all levels, not just on the business level, but all levels of with the ML team, the ML focus, architecture, how it's measured, and how performance is graded. So on this slide, I have a bunch of charts. I'll just focus on the left-hand side. So on the top left is the cumulative gains chart, and the bottom left is the ROC curve. So I'm showing you this contrast. So these 1, 2, 3, 4, 5 are data points that roughly correlate to the same point across the charts. And you can see that they're not at all one-to-one, right? And this is important because currently many data scientists and machine learning folks, they use abstract measures like ROC curves, confusion matrices, etc., to evaluate what's the best model. However, it's very, as you can see in this case, this doesn't necessarily translate into a real world or tangible business benefit, right? Because whereas the gains is a very tangible based on real world business metrics, ROC is very abstract. So it's always important to use real world metrics for evaluation to size business improvement and impact. So for example, I had a team member, who was telling me that he was very confident in his model because it was, close to 0.8 AOC score. And I made him profile it by the gains and deciles, and it was actually flat. So he had to redo everything because it was not the right model for the situation. It was not performing the way the business needed, even though it performed well on the abstract score. So on the right-hand side, you can see that I talked about prioritizing model efficiency and model accuracy. And this basically, rather than obsessing over accuracy or accuracy type metrics alone, we also need to think about the efficiency of the model when it comes to production and scoring. So for example, I had a model that took over 12 hours to compute. And when we reduced it to a subset of features, it only took half an hour with only a marginal accuracy loss. So you can, obviously, it's a no-brainer which one you want to put in production, the latter one, because it's going to compute much faster, which means it's going to be less error and you have free up more resources for other things. On the bottom right chart, what I'm trying to explain here is that we need to right size the model based on deployment needs. So for example, if your model is going to be deployed monthly, you can get away with a more rigorous, higher accuracy metric because it's not going to refresh that often, it's not going to tax the system as often. But as it becomes more frequent, up to say daily, you need to set that your model efficiency has to be more important than your model accuracy because you need to free up resources, first of all, for that pipeline to finish running, but also recognize that you can never attain the same accuracy levels as, say, a monthly model because daily data is way more unstable and way more noisier than aggregated level data such as a monthly. So what this means is focus on being dependent versus distracting. And what this means is sexy sells but seldom delivers. And so I think from executive to execution mindset, that mindset is a shift to being what's dependable and what actually can accomplish the job versus just what's new and sexy for the sake of it. And secondly, Know the limits. So do you have the right data to solve the problem? What is a realistic expectation for like performance? So I think being very critical and very clear on these things will put you in a better stead to scale up your own team to deliver business impact. Thank you.